Yeah, hello everybody. So my name is Gero Flucke, as said, from the European XFEL and the controls group. And I'm happy to share with you some experience we had with data logging to InfluxDB. So I want to first introduce what data logging means and how it fits into our Karabo control system that Stefan talked about yesterday. How we map from Karabo entities to Influx database, show the database setup we had, and also give you some insights on hiccups on the way before I conclude. So come back this year. Karabo is our control system. It's device-based communication via message broker, where we have a main entity are the self-describing devices for equipment control for motors and pumps, data acquisition like cameras, also an online analysis mode can be in there, or data logging, which is the topic of this presentation. And there are other system services, GUI server for the graphical user interface, or we have data acquisition that is for big and scientific data. As you see here, there's also data flowing not by the broker, but TCP IP direct pipelines for camera data or big ADC data, which is not the topic of this talk, but we are talking about data logging for slow control or the thing that go by our broker. So the main use cases of log data is in the control system to get historic data for trend lines. So you want to see, for example, the last week's value of some property of some device. In this case here, it's some gauge where you use 1 week of data and you get here some curve. Or we want to see what has been the configuration yesterday or 5 days ago, because we want to compare to what is currently the case. So you select here, specify time point, and then you can see data arriving and see, okay, there was some configuration different, and now you can choose, see what is a real one. So how does the data logging now integrate in this event-driven broker communication? So we do this via a cross-device signal slot subscription. So there are devices interested in some properties of another device, so they subscribe. In this case, you have 3 devices interested in this one. And then if that device updates some of its property, it will emit a signal to the broker. A single message will go to the broker, and all the others get informed about this. So by this, you avoid overhead for publishing for these popular devices, which many others have interest in, and the polling on the control system level is obsolete. Now, as I said here, it's used by the data logger devices, where the logging task then is distributed in one communication entity among a handful of logger devices, and they subscribe to property updates and schema updates. So the schema is a self-description of our devices. And each of these loggers subscribe to their share. What do we log then? It's all these properties where we do not really distinguish here between configurations like the hardware port of a camera, or some conditions like a value read from the hardware, like a temperature. And also this self-description, the schema is stored, and the timestamps are propagated to the system from the original device, and then they are stored in the database. So how is this done? So just from history a bit, we had a custom-made solution from 2014 with an ASCII file backend, where there was a directory for each device being logged, and then you had a timestamp in different formats, the name of the property, its type, value, and some metadata. Of course, human readable data is nice, but it has, of course, drawback. It doesn't scale well. So we stored only 3 months data available for quick lookup, and then archived away. To get the indexing right was some endeavor. It worked in the end, but okay. And we had no support for statistical treatment if you receive data of a week, and probably the number of points there are too many. So you want to have some averaging or something that was very sillily or easily done. With just downsampling is thrown away every second, or even 5 or 6 points, depending on how many points you have there. And then, of course, it can be very slow. So a time series database fits well to the event-driven Karabo. So our has the endeavor started with the prototype in 2018, a series development in 2019 and 2020. And it's in production since summer 2020. And we migrated all data from January 2020 onwards into this real database system. So how do we map data and entities from the control system to the database for the historic data? So we have this device-based control system. So, well, that fits very well. InfluxDB has a notion of a measurement, and each of the property of the device then maps to one field in there. Here's kind of sketch of this, or time, of course, not in this ISO format, but just a number. And then you have different fields here that this device might have. And the fields can update together with the same timestamp, or just this one you update, and then there's no data in here. There's one subtlety. So the fields within a measurement must have a unique type within a shard of the database. It's a time period the database puts it like a basket. Data here and future data will be somewhere else. And within such a shard, the type has to be the same for each field. But in Karabo, we allow devices to update or to develop. Maybe developer of the device decided integer was not a good choice for this property, it's a float. So we need to have some schema evolution be working, and that's why we had to add to the field name of the Karabo property also its type, and then if something changes, you can distinguish what the type is. Similarly, you might want to also log whether some property is floating point is not a number and infinity, because that may be the cause of further trouble elsewhere. And floating point values in InfluxDB don't like not a number, so we have another field here where the field extension is then float in instead of the simple float there. As said, so the timestamps are received from the device itself. We store in the database in millisecond precision, and we also store our XFEL internal photon train ID if provided by the device. Mapping of the types is at first and very simple. So there's a bool in Karabo and a bool in InfluxDB. We have float and double distinguished in Karabo. There's just a float in InfluxDB with the caveat of the special not a number treatment that I mentioned. Various types of integers that we have in Karabo, which all map fine to the integer that InfluxDB provides, except that InfluxDB stores integers as a signed 64-bit integer. And if you have an unsigned 64 integer, then you have to do something. So what we choose is just to reinterpret and read back. We have to back interpret that. And strings are, of course, naturally also in the database, but new line characters and so on make trouble in the transfer protocol. So we have to mangle these. Strings are, vectors, sorry, are not as such supported by this database, or a little drawback there. So what we do is we make a comma separated string out of them. So it can still be interpreted well outside Karabo. The vector string is a bit special. If you want to distinguish an empty vector of strings and a vector with only a single empty string inside it, you have to do something, and they're decided for base 64 encoded JSON string. So that's all the data that can also be interpreted without Karabo. And then there are the Karabo specific data types for raw data, which is rarely used. Our table data and the schema self-description, where we serialize this to binary and then base 64 encode. So that is now the setup as we started with. So the Karabo side on the left, communication around the broker, where we have in fact 6 brokers for over 12 communication topics. 20,000 roughly devices all around, distributed among all these communication topics with together about 2 million properties. And in fact, 75 of these devices are the data logger devices, which send the data to an ingest agent for the real database. It's Telegraph here, where in the beginning we had exactly one object here. Now, the 12 communication topics map to a database inside InfluxDB, and then the data from the ingest agent Telegraph goes to two places. One is a cluster of 2 InfluxDB nodes, so it's an enterprise edition that we pay for support and so on. And the second InfluxDB, which was using the open source edition, and that is then used to access data also outside our control system with the Grafana tools, web data visualization, which is very, very powerful. But we wanted to decouple this from the control system because we could not really judge how much this will be used in the very beginning. So whenever this might be overloaded, the control system is still fine. So there is an enhancement of the operational experience as we hoped for. So we can provide much longer data availability than previously. So 3 years retention period was decided upon and will become active end of this year. While the InfluxDB readback mechanism allows directly to average data, so we do not simply have to downsample. It's rather fast data retrieval, and the availability of data for the Grafana web frontend opens doors beyond the control system, many visualization options for detailed data analysis. And then there arose a new use case. So the facility started a data operations center, which wanted to monitor all the systems continuously for best support of the scientists. And this was chosen to monitor the data there. And well, it's feasible because it's about 30 seconds delay in all this monitoring process. Yeah, let's skip this here. There have been hiccups on the way, of course. So first, beware, Influx is a sharded database, I said in all the chunks. And if the writer has to flip back and forth between jumps between the buckets, because one device may have a bad timestamp, we have seen even years in the future somewhere, and then it's really has to swap back and forth, and the delay of the data availability is there easily beyond an hour. And then more at the beginning of this year, or maybe the end of last year, we saw some time to time, out of a sudden, some failures here of our ingest agent, the Telegraph thing. And while we were debugging and trying to understand what this is, we said, okay, maybe it's not a good idea to have only a single one there. We share the load of our 3 beamlines now between 3 instances, and they all right there. And in the case the problem still appeared, well, at least only 1/3 of the facility is affected, not everything. Then to debug, well, it's always a good idea to monitor nicely also instances that do the service, the network performance, memory, CPU load, etc. And in fact, what we could see here when there's an incident in April, the input rate is rather stable, this lower line here, but with this large spike, 150 megabits per second suddenly, and then another one, and the output to the real database constantly high. So what's going on there? Luckily, before the database for the data that we wanted to save really goes down, some data is there, and we have a very sophisticated Flux queries and can be done by Grafana to the InfluxDB that you can really figure out what's going on there. And there was some schema update rate of more than 30 megabytes per second updated within average over a minute. So what the hell is this? But first, what are the findings then? InfluxDB could not cope with data rate from Telegraph. It replied with an HTTP error back to the Telegraph instance, which said, okay, an error, also I have to try again. An error again, try again. And then it was busy with sending this big data, which could not be handled by the real database backend. And the new data that arrives just piled up in the memory and suddenly it goes down. Unfortunately, if the telegraph instance has to go down, the data in the buffer is lost. Well, in fact, we trace this back to 2 bugs on our side. And really the conjunction of the 2 bugs made the problem explode the things. So one is that there's some device that was updating its device schema 180 times in a loop instead of looping and then updating at the very end. And then the bug in our logging device where some buffer is used, where the serialized schema is in, and well, it was just a bug that the buffer was not cleared when the new schema comes, so it just depends. And then you have 180 times and it uses 180. So it's an n-square problem. And it showed that, well, it's nicely that we are event-driven, but we have to prepare ourselves because otherwise a single ill-behaving device can compromise the logging system, and the protections are then put in place in the Karabo data logger system with 2 long vectors, schema update rates for every property, and we keep track of refusals to identify these badly behaving things. Just in numbers, so roughly we have each of the 3 telegraph instances at 10 megabits per second. But of course, if there's a summer maintenance period, there's less, and we shut down things and slowly ramp up. And so far we have stored 25 terabytes of data for each of the nodes, with a redundancy of 3. There are some future steps where, in fact, the cluster that we had originally here, we want to split up. There's not much gain of the cluster, but we have want to keep the 2 instances here. The instance that is mainly used for monitoring will have a shorter retention period here only because otherwise sometimes the reaction is slow. The Grafana will use a cluster of 3 devices. It's still open source. And also all these influx databases will upgrade to the same version, all enterprise edition. So to conclude, since 2020, European XFEL streamlined instrument control logs, slow control data to influx database, both configurations and conditions. We have 25 terabytes on disk. We have experienced really nice, quick retrieval of data, and really flexible queries are possible. And this allowed our data operations center to monitor constantly there. Datalogging to InfluxDB itself fits well to Karabo, but we need protection against behaving noisy devices. And well, no bugs, please. And finally, logging to InfluxDB boosted the availability, accessibility, and usage of historic control data as European XFEL. Thank you.
Thank you very much for your presentation. We've got room for 1 question.
I can shout it out. Okay. So the influx database, is that a standard SQL database, or is it a more specialized time series database that you use some other query language to?
So you can query with something that is like SQL query, but the database behind is structured, well, basically, if you want to have some tables here, there are these holes in there. If there's no data, then there's really no data. It's just indexed. But what is very good is, so you have also this, this flux query mechanism, which is a more advanced querying language, which is very powerful and allows really to correlate all from different measurements, so Karabo devices, the data.
Thank you again.